Welcome to this class. In this session, we are going to discuss about conservative vector fields and scalar potential functions. We'll do some examples. So, conservative vector fields. So we start by defining what we mean by a conservative vector field. So definition. So a vector field F is called conservative if there exists a scalar function F such that this vector field can be expressed in terms of gradient of this scalar function. So this is the definition of a vector field which is conservative. So a vector field which can be expressed as gradient of a scalar function is called a conservative vector field. And then in this case, the scalar function F is called the potential of the vector field F. So we have two main things that we have defined. One, conservative vector field, which can be expressed as a gradient of another scalar function. And then this scalar function, which satisfies this equation, is called the potential of the vector field. So let's do two examples to illustrate how we find the potential of a vector field if you know the vector field. So examples. We'll do two examples in this class. So example one, find a potential for the vector field F given by 3 plus 2xy I plus x squared minus 3y squared j. So these are the question to find a potential for this vector field 3 plus 2xy I plus x squared minus 3y squared j. To solve this question, we have to remember the definition of a potential with respect to the vector field. So solution, we know that a potential exists potential function f for the vector field f exists if and only if this vector field is the same as gradient of this potential function. So this is by definition. So next we say, so this is the same as now, because this is 2D, then we write the gradient of this scalar function or this potential in 2D. So it's the same as partial f partial xi plus partial f partial y j should give us 3 plus 2xy I and then plus x squared minus 3y squared j. So we're just putting the values into this definition. And so for equality to make sense, then the component of I on the left should be the same as component of I to the right. Component of j to the left must be the same as component of j to the right. Partial f partial x equals to 3 plus 2xy, and then this partial f partial y must be equals to x squared minus 3y squared. And then we call this one equation 1, call this one equation 2. So our interest is to find the value of f. So to find f, if we take equation 1, then to get f on the left-hand side, we have to integrate with respect to x. So we say integrating both sides of equation 1 with respect to x, we get, so we integrate partial f partial x with respect to x. We also integrate this side 3 plus 2x y with respect to x. So now when you integrate the left-hand side, you get f equals to, so this will give us 3x plus this one will give us, so 2x squared over 2. So this will have x squared y, and then plus constant of integration. But then now this constant of integration, we write it as a function of y. So call it g of y. Call this one equation 3. So the interest will be now to find this value of this constant of integration. So if we know the value of g of y, then we'll have our f. And then we now say differentiating both sides of 3 partially with respect to y, we get partial f partial y. So this, because this doesn't have a y variable, should be 0. And then this will give us x squared. And then this one now will give us g prime of y. And let's call this one equation 4. Now we have equation 1, 2, 3, and 4. But if you observe these equations 1 up to 4, then you find out that also equation 2 is defining partial f partial y. So therefore equation 2 must be the same as equation 4. We say equation 2 equals to equation 4 because all of them are defining partial f partial y. Now equation 2 is given by x squared minus 3y squared must give us x squared plus g prime of y. And then in this equality, x squared and x squared cancels, so that we have g prime of y equals to minus 3y squared. And so call this one equation 5. Now to get g, we simply now integrate both sides of this equation 5 with respect to y. So integrating both sides of 5 with respect to y, we get integral of g prime of y dy equals to the integral minus 3y squared dy. And so with g of y will be given by now, this will give us minus y cubed, then plus constant, say k. So k is the constant of integration. And then now from this value of g of y and what we had found here as our f at this point in equation 3, then we see that f will be given by 3x squared, 3x plus x squared. So therefore, from 3, f is x squared minus 3x plus x squared y and then plus g of y, which is the same as minus y cubed then plus k. So therefore, actually the sign here is plus. If you just check the f function here, now this plus. So therefore, this is the required potential function. So this is the required potential for that given vector field. Now, example 2. Find the potential function for this vector field f given by 3x squared plus y I plus 2x y plus 5 j. So find the potential function for this given vector field. So from definition, we know that the vector field f equals to gradient of the potential function f. So which means we'll have 3x squared plus y I plus 2xy plus 5 j equals to partial f partial x I plus partial f partial y j. So this is the definition of the gradient of this potential function for this scalar. So for this equality to make sense, then partial f partial x must be 3x squared plus y. Call this one equation 1. And then partial f partial y should be given by 2xy plus 5. So call this one equation 2. So to get the value of f, we start now by integrating this equation 1. So step 1, integrate both sides of equation 1 with respect to, so to get f now should be with respect to x. So IA will have integral partial f partial x dx equals the integral of 3x squared plus y dx. And then let's carry out this integration. So on the left-hand side, we'll have f, because now this and this cancel out. This is the inverse of this. So we'll have f equals to this with respect to x will give us x power 3 plus xy, and then plus. Now there's a constant of integration, but then that constant of integration, because we're dealing with the function of two variables, we write it as g of y. Call this one equation 3. Now, next step, we now differentiate this one again, but now with respect to what? So remember, if we know the value of the function g of y, then we'll have our f, but we don't know the actual value of this constant function of this value g of y. So integrate, differentiate both sides of 3 with respect to y, i.e., we have partial f, partial y. So this will give us 0 because there's no y here. Here we'll get x, and then plus g prime of y. So I'll call this one equation 4. And then now, if you observe keenly, equation 4 and equation 2 are the same because all of them are defining partial f, partial y. So equation 2 equals to equation 4 because all of them are defining partial f, partial y. So therefore, let's equate the expression for partial f, partial y in equation 2 to this equation 4. And equation 2, we have 2xy plus 5. So I'll have 2xy plus 5. That should give us x plus g prime of y. So this will make g prime the subject. So we'll have g prime of y equals to 2x y plus 5 and then minus x. Call this one equation 5. Now to get g of y, we simply now integrate this equation 5 with respect to y. So integrating both sides of 5 with respect to y, we get so we'll have integral g prime of y dy equals to integral of 2x y plus 5 minus x dy. So this will give us, so here we get g of y because now this is the inverse of this. This with respect to y will get now x squared. Will be simply x y squared because now we have 2 power 2 then dividing by that's 2. Cancel these 2. And then plus 5y and then minus x y. Then say plus constant of integration. So I'll call this one equation 6. So now remember from equation 3, we know what f is. So equation 3 using 6 in 3. Equation 6 in 3. Then f will be given by, so 3 we have x cubed plus xy and then plus g of y, which will be plus x y squared plus 5y minus xy plus k. And you see this and this will cancel out. This is positive, this is negative. So therefore, our potential for this vector field will be given by f, I can say f of xy equals to x cubed plus x y squared plus 5y and then plus k. So this is the potential function for the given vector field. So in the next session, we'll give other examples on determination of the potential function. Now, a case whereby we have 3 dimension, where you have the I, J, and K vectors defining the vector field F. So thank you.